Hello and welcome again to the series which is on machine learning fundamentals. We were on a very critical stage where we were discussing, in fact, oversampling techniques, and we had discussed smooth and random sampling and synthetic minority oversampling technique. So now we are going to discuss adaptive synthetic sampling, and yeah, we'll be giving certain examples in this one, and then we'll take some related aspects before moving on to implementing this adaptive synthetic sampling in Python. So there is one very good example which is shown on Python, which will be in fact showing the practical aspects of adaptive synthetic sampling and in what scenarios or conditions we can utilize this and how it is proving to be fruitful. So coming to this adaptive synthetic sampling, adaptive synthetic sampling generates more synthetic samples in regions where learning is difficult. If we are comparing it to smooth is in fact, synthetic minority or sampling technique is generating the samples and making the minority samples equivalent to others without any other criteria. So it is actually it is not duplicating the values like we are having random sampling, but what it does is it is inserting the other values which are not duplicate of the minority class, but it is randomly putting those values and inserting them. But as far as the adaptive synthetic sampling is concerned, it first of all analyzes the data. The minority data is being analyzed first of all, and then it checks that which are the points where we are having which are having missing data, where nothing is there. So those points, those data points in minority class should be filled. So in adaptive synthetic sampling, generates more synthetic samples in regions where learning is difficult, because we are not having values here. The minority, there's a minority class, definitely those that minority class is having less representation, it's not there. Unlike smooth is having the uniform approach. It will be adding the samples. It will not be a duplication of the values like random sampling, but it will be adding values, but irrespective of which particular place, or which regions are there, irrespective of the regions. So adaptive sampling uses adaptive density based sampling that focuses on how to learn minority points near decision boundaries. So you are having near decision boundaries where you are not able to segregate, for example, a majority class with a minority class. You are not able to, for example, in certain cases, some example which we have taken earlier, you are not able to segregate, for example, what is a fraud and what is a normal transaction. So those boundaries which are there, those boundaries it is filling. This adaptive emphasis on complex boundary areas makes it ideal for the overlapping. So definitely it is on these areas where it is filling, where it is difficult for a machine learning model to decide whether a particular transaction is a fraud transaction or it is a normal transaction. So it will be filling that minority class. There will be better representation of that, and it will be making ideal for overlapping. So definitely there can be a possibility of overlapping in this. So comparison of oversampling methods. So if we are comparing these three methods which we have learned in the oversampling. The first one was random oversampling. It duplicates existing samples, simple and fast, but risks overfitting and best for small data sets. So our random oversampling is best for small data sets because it is simply filling, randomly choosing the values, and it is adding the duplicates randomly from the existing samples itself. So it is there's a risk of overfitting in this, as we had discussed earlier as well. Comparing it to smooth, if we see synthetic minority oversampling technique creates synthetic samples via interpolation, better generalization, but may introduce noise, idle for general purpose use. So it may introduce noise, which can be in fact problematic, and with that as well, there can be it is better way of actually generalizing, If you are creating a synthetic samples, and it is using interpolation for that. Now, better generalization will happen, but may introduce noise as well. So there is a chance of, little bit chance of overfitting here as well. But it is ideal for general purpose use. And comparing these two with, if all of them, then we are having one more comparison, which is with adaptive sampling. Adaptive sampling focuses on difficult regions, so it is concentrating and focusing on those regions where it is very difficult to differentiate a minority class with a majority class. So it can be on the boundaries where, representation of minority class might be less, and then it is filling those gaps. Handles complex boundaries, but computationally costly. So what is there in adaptive sampling? It is actually, it tackles the this data, unbalanced data very well. And it is in fact having, it does not introduce noise. It is actually focusing on those areas where representation of minority class is less, where it is difficult to segregate and differentiate a minority with a majority, those boundaries which are there. So in that particular way, it is very efficient, but at the same time, it can be computationally costly, because this particular sampling method will be utilizing more computational resources. So there is in fact definitely a, you have to just see and balance between the computational cost and the performance, efficiency, performance, and uh, uh, overall accuracy of the machine learning model. So that is there. So this was the comparison, and you can just see Python setup. I'm going to show you program directly. I'll show an exhaustive program which is on. I had shown earlier one which was on Smooth, and then we are. It's actually the code here which it is showcasing for these, and oversampling here as well. So it is showing the code. In fact, we have done one program already for we have done one comprehensive program for Smooth. I'll be showing one more to you for the synthetic sampling. And if you see the performance comparison, side by side visualization of model metrics before and after Smooth our sampling. So if we just see synthetic minority or sampling technique, these are the comparisons which are their key improvements, including significantly higher recall for minority class detection. So definitely recall, which is there, so significantly higher. Improved F1 scores, balancing precision and recall, that is also there. And then enhanced AUC, ROC, which is very critical, demonstrating better class discrimination. And definitely it is also demonstrating that the minority class has been taken into consideration. And it's not just about accuracy, which can be 95 and then still the model is having no use, it is useless. But it will be improving the ROC, AUC, which will be in fact representing the better class discrimination. And confusion matrix heat maps reveal the dramatic reduction in false negatives after balancing. So that is there. It will be showing that confusion matrix will be showing that we are having dramatic reduction as far as the false negatives are concerned. And false negative is the one which it is detected as a normal traffic, for example in fraud detection, normal transaction, but it is actually a fraud transaction. So that is very critical in fact. So in case of fraud detection, if you are designating, predicting, or putting a particular transaction which is fraud, a normal transaction, it is very critical. That is very critical. If you are having a false positive, a false positive can be that a normal transaction is put as a fraud transaction. That also is not good for the overall this accuracy of the machine learning model, but it is still a little better in such cases where you are having something which is which is in fact a fraud, and then it is put in as normal traffic. So that is much more dangerous than something which is a normal traffic. You are detecting it as a, because we should not be missing any fraud transactions. That is something critical in fraud detection. In the same manner, we should not be detecting a patient patient missing and putting a patient's diagnosis as normal, and scanning as normal, and but the patient is actually a person is having a disease, so that is much more critical. But anyways, these, whether we are talking about false positives or true false negatives or false positives, both of them, they will be having repercussions, implications. That is something which we have to focus on. And this, in fact, these parameters are focusing on that. What accuracy insights? Accuracy may remain similar or slightly decreased after oversampling. This is expected as the model now focuses on both classes equally. So recall improves significantly for minority class. AOC score increases, showing better discrimination between the classes. Model becomes practically useful, because we had seen the cases where, even if the accuracy of the model was 95%, but the usefulness of the model was zero, because it was otherwise as well. In case of fraud detection, 95% of the traffic transactions are actually normal, so 5% are fraud. But if the model is putting all of them as normal, so it will be still getting 95% of accuracy. So in that case, this is, model becomes practically useful. So for real world tasks, understands the trade-offs inherent to imbalanced learning scenarios. So definitely it becomes fit for the scenarios which we had discussed earlier. And then fraud detection, real world applications, fraud detection, medical diagnosis, cybersecurity, catch real fraudulent transactions in financial systems. Imbalanced learning helps identify 0.1% of suspicious activities that cause significant losses. So you can just see that early identification of rare diseases where positive cases are scarce, critical for cancer detection and genetic disorders. So, detection intrusion attempts, for example, in cybersecurity, and anomalies in network traffic, quality control for finding manufacturing defects in production lines. All of these are the real world applications and use cases. Stratified splits, best practices and recommendations. Stratified splits, what does that mean? Always use stratified splits to preserve class distribution. Apply or sampling only on training data, never on test data, to avoid data leakage. So definitely you should not be applying or sampling on the test data. It should only be on training data. There's a possibility of data leakage, which we had discussed earlier. Track multiple metrics. So recall, F1 score, AUC, not just accuracy. So use stratified cross validation for robust evaluation. Combine or sampling with ensemble or cost sensitive methods. So definitely you have to combine or sampling with some ensemble methods, so that you can or some cost sensitive methods. Experiment with different or sampling ratios and validate on real data. So this is combined techniques can sometimes be very beneficial as far as machine learning is concerned, and they can in fact yield a lot of benefit, in fact, as far as overall improvement to the model is concerned, and the results that are achieved. So monitor metrics as well, track multiple metrics. So you have to monitor metrics as well. We have discussed them in quite a detail. For example, F1 score, there can be inferences that can be drawn from these critical metrics which are there, and those inferences are very valuable. They are very critical when it comes to deciding overall performance of a particular machine learning model. So AUC, not just accuracy. Accuracy is not the only factor. We have seen that accuracy will not be in certain cases which we have discussed. Those applications, accuracy is nothing. So AUC will be taken into consideration. A stratified cross validation for robust evaluation. All of these things, in fact, we have discussed them. So they will be there. What are the key takeaways? Critical challenge: smooth works, validate properly. Imbalanced data significantly impacts machine learning model that we have seen. So imbalanced data can significantly, impact machine learning. It can render a machine learning model useless, that we have learned yesterday, in the previous episode. You should be always, taking other things into consideration. not just the accuracy alone, but accuracy alone can be misleading. We have seen that as well in the previous episode. You have to take other factors into consideration as well: AUC, recall, F1 score. Oversampling balances data sets and improves minority class detection. Smooth creates effective synthetic samples for better generalization. So smooth works, definitely it is, it works in most of the cases. Validate properly. Proper evaluation matrix and stratified validation prevents overfitting. Combine techniques for best results in production. So you need to combine the techniques. Before I wrap up this particular uh, you know episode, I would like to showcase you one a very good program which is on adaptive sampling. So you can just, I'll just explain it first of all, and then I'll be running it. This is the, your adaptive synthetic sampling example. So, if, for example, for this running this program, you might need to install the imbalance learn, which might not be available there. So you have to just say pip install this Im, uh, imbalance learn, so that it will be able to install this. So, and from there we have to actually import this adaptive sampling from imbalance.our. We are importing it from imbalance.our sampling import adaptive sampling. So this might not be installed, so you can just see that. Then we are creating the imbalance data. You can just see there 90 and 10 is the 90% majority, 10% is minority. And then we are having, in fact, we are printing this class distribution, and then we are plotting a figure of this. So you can just see this. So we are having 7 by 5 figure size. So that is what it is giving, and then we are putting in x and y values there. If you just see, x and y values are there given with this one. So this is something simple we have done before as well. So x-axis, y-axis labels are there, which have been given figure 1 and figure 2, and the title of this figure will be original imbalance data set. This figure will be giving us, how the original data is. And then we are using the adaptive sampling. Sample strategies auto, so it will be automatically fixing and neighbors which are there, that 5 points it will be seeing near to a particular minority, and it will be just, seeing that those 5 points and putting values in those if they are not, for example, available there. So it will be filling in a different manner, not as randomly as other techniques which are there. Simply adding synthetic values, no, it will be just checking the minority class. It will analyze first completely, and then based on the deviation from the point which is there, it will be filling the data there. It will see the borders as well, as we have said that, between two classes, the boundaries which are there, which which where we can have a difficulty in segregating from fraud from a normal this for example transaction. So in those boundaries as well, we are overlapping is also, it can happen. So there are chances of overlapping. So it will be in fact, distribution, it will be printing class distribution after, and then it will print that reassembled data, and then it will be drawing the figures on this one. If you just see, it will be it will be in one row, it will be putting the values of x only, and then in one more label it will be putting the another row. So it will be that means, minority and majority class will be represented by this one here. And then alpha is equal to 0.5 will be, it will be putting it, this is the transparency which will be there. So transparency is 0.5, so that is about this plot. And then it will be putting these reassembled resampled ones. So that is the normal one which is there, and then reassembled ones which are there. Minority class after this, so it will be printing this majority class, it has printed now minority class, and here it will be putting the transparency as 0.8. So you can just visibly see that, from that plot which will be drawn, you'll be able to see what exactly, is a minority class and what exactly is a majority class. It is giving a different transparency to both of them, and this is simply the x label, y label, and the data after adaptive sampling or sampling. technique is used, and then it is printing reassembled data set and the original data set which is there. So let us just go and fill it up. Most of the things which you have seen in the program, we are known, those are known to you, because we have discussed them in previous programs as well in detail. But here I'll just get this terminal window up so that you'll be able to see the results with a better view. Run without debugging. I'll use the Python debugger, and I'll say that you run this. Let us see what happens here. And here we go. We are having, first of all, it's saying that original class distribution, so counter, and it is giving the 449 as the class 0, which is a majority class, and then 51 as a minority class. There is a huge difference between the two. So then it is showing us, if you just see, it is showing us the graph here. So I'll just drag this graph for you. So it's showing a original imbalance data. So you can just see this is a majority class which is with the blue, and there is a minority class with the orange. If you just see, that's nothing. So minority class is 50 values only. So we can just see feature 1 and feature 2. If I'm closing this particular graph, then we are having class distribution after we are applying the adaptive sampling. So what happens is we are getting the majority class which was there 449, and we are getting the minority class as well for 444. So it is near to this, so it's almost same. And the graph which is there, data after the adaptive sampling has been implemented, you can just see this is coming as now minority class after. So you can just see the better representations of this, you can just see. And they are falling on, you can just see they are falling on the similar points which are there, because it's filling those points which are nearby points which are there. So it is putting them, they are not randomly as we have seen in the previous technique. So when I close this, it will be giving me original data size was 502, and then the resampled data size is 893 with 2. So you were having 500 total values if you see the original data which was there, because it was for 449 and 51. Then the reassembled or the adaptive sampling technique, when we use the reassembled data which was there, that became 893, 449 and 444. So if you just see, that becomes 893 in total. So this is how it is. And I think we can just in fact see that what kind of improvements, if you just see AOC or OC can also be, because this was for the visualization only. So it is more for the visualization, so that we can get better visualization of the results which are there. But visualization showing that what is the majority class, and where is the minority class, and what happens after you are applying the so it was showing with that graph which was there, that how the points were added with the adaptive sampling. But interpretation of the results here, we can just definitely we can just test give a different value, and on that predictions can be made, and then we can just see what are the results and the interpretation of those where it is making it. That we have done already with the smart, in fact, in the previous episode. So I hope that this will be sufficient. Maybe we'll be doing one program more, or maybe later on when we finish it off, we might be having a scenario in which we'll be implementing this. We'll be using anyways synthetic this or sampling, whether we are talking about smooth, we are talking about adaptive sampling. More smooth is used and preferred in many cases, and adaptive sampling, if for example we'll be implementing this in different scenarios based on the requirements as we are implementing and using machine learning. So this is something which you are going to use frequently as well. Thank you so much once again for connecting, and I hope that this topic, very interesting topic of or sampling, we have concluded this. And on the other side, we shall be taking now from this point onwards, we should be taking in fact other machine learning algorithms, significant ones which are there. So for example, KNN, SVM, and the algorithms like that. So those will be discussed in the series to come. Thank you so much for joining, and please provide your critical feedback. Your feedback is very valuable to us. We'll be able to make enhancements in this particular series, which is going now, very interesting. And not only in this, but the series which are there to come as well, whether they are in the area of artificial intelligence and machine learning, or in the area of cybersecurity, we will be definitely implementing those suggestions you'll be putting forward, and we'll try to enhance, in all those aspects which are given to us, suggested to us by our valuable viewers. Thank you so much once again for connecting.